Okay, so this is another lecture over spectroscopy. So in this lecture, we'll cover what's known as IR spectroscopy or infrared spectroscopy. If you remember from the first lecture over spectroscopy, it's a good method to determine what functional groups or what functional classes in a molecule. So in terms of IR, so you have what's known as far IR, mid IR, and near IR. So far IRs, so if you remember, lambda is wavelength, so from 400 to 10 inverse centimeter, or from 25 to 1,000 microns, so micrometer, same thing as microns. So that's really not used in this type of IR spectroscopy. You have what's known as mid-IR, which is 4,000 to 400 inverse centimeters, and we'll explain what inverse centimeters is in just a minute. So that's from 2.5 to 25 microns, and so this is the most useful region of the IR region for an organic chemist. So that's from frequency, so 1.2 times 10 to the 14th hertz to 1.2 times 10 to the 13 hertz frequency radiation. So this type of IR radiation causes molecules to rotate and their bonds to start vibrating and bending. And then you have what's known as the near IR, which is not used for IR spectroscopy either, but that's from 14,000 to 4,000 inverse centimeter wavelength, or from about 0.8 to 2.5 microns. Okay, so any two compounds except for enantiomers are unlikely to have the exact same IR spectrum. So IR is like a fingerprint for a molecule. So a detailed analysis is usually not needed because there are other spectroscopic tools like NMR that we'll talk about soon that gives more detailed information about the molecule. But IR is a pretty simple technique to use. 5 minutes, you can record an IR spectrum of your molecule, and it'll give you this important information like what functional classes in your molecule. Does it have a C double bond O, an alcohol, or an amine, so forth in your molecule? Okay, so for a vibrational mode of a molecule to be IR active, it must result in a change in the dipole moment of the molecule. Otherwise, that vibration or bend is not an IR active, but you could observe it using spectroscopy known as Raman spectroscopy or rotational spectroscopy. So there's two types of vibrational modes. You can stretch bonds and you can bend bonds in a molecule. So linear molecules have what's known as 3n minus 5 vibrational modes, where n is the number of atoms in a molecule. And nonlinear molecules have 3n minus 6 vibrational modes. So if we take water, for example, so it's got 3 atoms. So 3 times 3 is 9, minus 6 is 3, so it's got 3 vibrational modes. Whereas a molecule like dichloromethane has 5 atoms, so 3 times 5, 15, minus 6, it would have 9 vibrational modes. So you could potentially see 9 peaks or 9 signals in your IR spectrum. A linear molecule like CO2, so 3 times 3 is 9, minus 6 has got 4 different vibrational modes, and we'll look at what those modes are in a little bit. So for water, for example, 3 vibrational modes. So basically what happens is you shoot an IR beam at your molecule, and that causes bonds to start bending or bonds to start stretching. So one of the 3 vibrational modes is what's known as the bending mode. So if we took this OH bonds and bent them towards each other, then that would be one of the vibrational modes. And so that occurs at 1960 inverse centimeters, so that's a low energy compared to the other ones. You have what's known as a symmetric stretching mode. So if you have the water molecule and you start stretching the OH bonds in the same direction at the same time, then that's what's known as a symmetric stretch. So that occurs at 4,049 inverse centimeters. Or you can have what's known as the asymmetric stretch. So if my hands are the two hydrogens, so if one of them compresses and one of them stretches, and the oxygen of course is up here, then that would be the asymmetric stretching mode, and that occurs at 4084 inverse centimeters. Okay, so what's an inverse centimeter? So this is the unit that's commonly used in IR spectroscopy. So inverse centimeters is what's known as a wave number. So it's just 1 over centimeter. So if you remember what wavelength is, so IR propagates, it's one of the electromagnetic radiations. So light propagates as a wave, and so wavelength is the distance between any two solar points on the wave. Right, so it's a distance. So for example, it could be centimeters, and so if you took that distance and took the inverse of it, also 1 over the wavelength, that's given this symbol. So that's what's known as wave numbers. So as wavelength increases, energy of a wave decreases, right? But since wave numbers is inverse wavelength, then as the wavelength goes up, inverse wavelength goes down. And as wavelength goes up, the energy of electromagnetic radiation goes down. Okay, so this is what a typical IR spectrum would look like. You basically just have different peaks or different signals on the IR spectrum, and interpreting those signals based on where they're at tells you some information about the molecule. So for water, if you took water's IR spectrum, it would look like this. It's going to have 3 different signals, one for the bending mode, the symmetric stretching, and the asymmetric stretching mode. So in the IR spectrum, the left is the high energy region and the low is the low energy, or the right is the low energy and the left is the high energy. So typically you see IR spectrum plotted from 400 inverse centimeters to 4,000 or 4,500 inverse centimeters. So for water then, you would see this asymmetric stretching mode peak at 4,084 inverse centimeters. 4,049 inverse centimeters, you would see the symmetric stretching mode. And at 1960 inverse centimeters, you would see the bending mode for water molecule. So if we took a linear molecule like CO2, then it should have 4 vibrational modes. So if you had CO2 molecule and you shine a UV or shine a IR beam on it, then one of the stretching modes is the symmetric stretching mode. So if the carbon's in the middle and these are the 2 oxygens, then if we stretch those 2 oxygens in the opposite directions of each other, then that is the symmetric stretching mode. And this is not observable in IR because CO2 of course doesn't have a dipole moment, and if you stretch those oxygens in the same direction, it still doesn't have a dipole moment because the 2 individual bond dipoles cancel each other out. So that mode is not observable in IR spectroscopy, but you would observe it in rotational or Raman spectroscopy. And so the energy required to make the molecule stretch like that is 1340 inverse centimeters. And then you have the asymmetric stretching mode. So if you stretch one oxygen this way and compress the other oxygen, so the carbon of course stays the same, doesn't move, but if you compress this oxygen and stretch that one, or compress this one and stretch that one, then that would be the asymmetric stretching mode, and that would result in a dipole change in the molecule. Right, since one of these would be getting bigger, bond dipoles, and one of these would be getting smaller if you compress this and stretch that, or vice versa. So that would change the dipole moment of the molecule. So that is an IR active stretching mode, and that would be at 2350 inverse centimeters. And then you have 2 bending modes. So if this was in the XZ plane, so if your oxygen's here and carbon's here and oxygen is there, so if you're moving carbon back this way and the 2 oxygens that way, then that would be bending in the XZ plane, and that requires 665 inverse centimeters IR radiation to cause that to happen. Or if you're moving these things in the XY plane, so if carbon's going that way and oxygens are going this way, then that's bending in the XY plane, and that is the same energy. to cause that bend. So these two are said to be degenerate because they require the same amount of energy for those two vibrational modes to happen. So if you took the IR of CO2, you would actually only see, there's 4 possible vibrational modes, but you would only see 2 signals because this one's not IR active, so you would see that one, and then these 2 are degenerate, so you would only see 1 signal for those 2. Okay, so the basics of how does an IR work. So you have an IR source, so you shoot generates an IR beam that you pass through your sample, and then the IR that comes out goes on and hits a detector. So the sample will absorb the IR radiation right at certain wavelengths if it corresponds to one of these vibrational modes, in which case all of the IR radiation at that particular wavelength would not make its way to the detector, so you would see a signal because some of that radiation would be lost because it's absorbed by the molecule. Okay, so if the wavelength frequency matches the vibrational mode, then the molecule absorbs the energy, causes bonds to stretch or bend. So if the wavelength is at a correct frequency or wavelength, then you have absorption. And if the wavelength or frequency does not match one of the differences in energies in the vibrational modes, then the IR beam passes through the molecule and hits the detector. So then again, your IR spectrum typically looks like this. We're on the y-axis is plotted the percent transmittance, so that's how much of that radiation is hitting the detector. So in a region like this, then 100% of that radiation is hitting the detector, meaning it's not being absorbed by the molecule. Whereas when you see a signal, then that means that radiation is being absorbed by the molecule at that frequency or wavelength. So not all of it is hitting the detector because the molecule absorbing some of that. And so that would be a signal. And then you want to interpret where those signals are at, and that tells you information about the molecule. Okay, so again, as we move to the left in IR, that's increasing frequency, decreasing wave number, or decreasing wavelength. Yes, so wavelength gets shorter, energy goes higher, and that would be increasing wave number. So again, typically plotted from 400 inverse centimeters on the right to 4,000 or 4,500 on the left. So you could plot what's known as an absorption spectrum instead, but you usually don't. So you could plot the absorption on the left versus the wave number. Which means it's a form of plotting wavelength or frequency or energy, right? So basically the horizontal axis is energy, expressed as wave number, typically in IR spectroscopy. So absorption is simply the logarithm of 1 over the transmittance. So you could plot them as an absorption spectrum where the peaks go up, but usually not. They're usually plotted as a percentage or a percent transmittance spectrum where the peaks go down. But they would be at the same wavelength or frequency or wave number in either case. Okay, so how do you actually go into lab and record an IR spectrum? So there's many different techniques now. You can do it in the solid state, gas state, liquid state, pure liquid, or it could be, if it's a solid, you could dissolve it into some solvent and then take the IR spectrum while it's dissolved. So if you wanted to do that, this would be how you would do that. You would record what's known as a thin film. So you can have sodium chloride or potassium bromide plates. So if you take that and compress it to high pressures, then it will go transparent. And so you can make transparent plate out of them. And then you just dissolve your compound in some solvent and basically smash it between the 2 plates so that you create a thin film. And then basically the 2 sodium chloride or potassium bromide plates is just a way to hold your sample as a thin film between them. And then you shoot an IR beam through the salt plates. So these are transparent, so they don't absorb the IR radiation, but your molecule in the thin film will absorb some of the IR radiation. So will the solvent that you use to dissolve it in. And then, of course, the IR beam comes out and goes on and hits the detector. So basically, you would put your put pure solvent between the two discs first, and then scan that, so you get what's called a background scan. And then you would put your sample between the two discs, and then rescan it, and then the software will subtract out the background peaks. It will subtract out the solvent and the air peaks, since it's going to get that information from the first scan, and it'll subtract those out, and the peaks that remain would be the peaks due to your sample. So if you do that, you just have to remember, don't wash the sodium chloride or potassium bromide disc when you're done with a polar solvent or something, or anything with water in it, because it's going to dissolve them, since those salts are water soluble. So there's a better way to do this, but it requires a more expensive instrument, and that would be to use, for example, a dual beam instrument, where you can so you basically have an IR source, and then you split the beam. And so one beam goes one direction, one beam goes the other direction, and then using mirrors within the instrument, you direct those beams to your sample or to your reference. So then you can record your sample and your reference IR spectrum at the exact same time, and then send those to detector, and then the software can subtract out the signals for your reference, for your sample and the air and the solvent. If you're using a solvent, it can subtract those peaks out, and then the peaks that's left displayed would just be the peaks due to your sample. Okay, so this is basically what you need to know in an IR spectrum. So the different functional classes have signals at different wave numbers. So for example, if you see a peak at 3400 in the IR spectrum, this is typically the energy required to stretch an OH or an NH bond. If you see a peak at 3200 in an IR spectrum, that's the energy required to stretch a hydrogen, a CH bond where the hydrogen is attached to a triple bond, or an sp hybridized carbon. If you see a peak at 3050, again, this is the energy required to stretch a carbon-hydrogen bond. But in this case, the hydrogen is attached to an sp2 hybridized carbon. Around 2900 is again the energy required to stretch a CH bond, but in this case it's an sp3 hybridized carbon. So most organic molecules have CH bonds, so you're always going to see peaks in this region from about 2900 to 3200. But where that peak is at tells you whether the hydrogen's on an sp3 hybridized carbon, an sp2 hybridized carbon, which would mean you must have an alkene, or an sp hybridized carbon, which would mean you have maybe an alkyne in the molecule. Okay, so at 2800 is again a CH stretch. So 2800 inverse centimeters is again the energy to stretch a CH bond. So all of these CH stretches are in similar regions, but exactly where they're at tells you what kind of carbon the hydrogen is on. So in this case, it's the hydrogen attached to a C double bond O, which would mean that's an aldehyde. Right? Okay, so 2200 is energy to stretch triple bonds. So CC triple bond or CN triple bond. So all of these are stretching modes. So if you have an alkyne, going to have a peak around 2200. Have a nitrile, going to have a peak around 2200 in the IR. So a signal around 1700 to 1800 is the energy required to stretch a carbon-oxygen bond. So what kind of functional groups have carbon-oxygen bonds in them? Right, you have acid chlorides, anhydrides, esters, carboxylic acids, ketones, aldehydes, amides. Right, so they all have a C double bond O, so they would all have a signal in that region. And this is about the order that they come in. So the acid chlorides are around the 1800 region down to amides. So aldehydes and ketones are around 1700, and amides actually a little bit shorter than that, around 1650 to 1700. And if it's an anhydride, then you have two different stretching modes. You could have this symmetric stretching mode, or you could have the asymmetric stretching mode where you're stretching one while you're compressing the other. And so you see two signals for C double bond O if you have an anhydride. Okay, so 1650 is the energy required to stretch a C double bond C. So if you have an alkene in the molecule, and then 4 signals around 1600 to 1500 is the energy required to stretch a C double bond C. But if it's aromatic, carbon-carbon double bond. And then lastly, around 1200 is a CO single bond stretch. Okay, so all of those are very characteristic. So it tells you a lot about your molecule, right? If you have a peak around 1750 in your IR, you have a C double bond O in your molecule. So if you're trying to figure out the structure of a molecule, you better have a C double bond O in it, right? If you had a peak at 2200, of course, it doesn't have to be exactly 2200, just right around that region. 2250, fine. But right around that region, you have a molecule with a triple bond in it. Okay, so the intensity of a peak is related to the polarity of a peak. Well, one more point here. So for those of you who want to go on to medical school, dental school, pharmacy school, you'll have to take an MCAT, a DAT, a PCAT entrance exam. And so you would just have to have this stuff memorized. So if you're reading a passage and it tells you that this molecule had a peak at 3350 inverse centimeters, then you should know right away that this molecule has an OH or an NH in it, right? So if you come up with some structure for a molecule and it doesn't have an OH or an NH in it, it's wrong. So what peaks are not there also tells you something about a molecule. So if you think you had a molecule that was an ester, but you looked at its IR spectrum and there was no peak between 1700 and 1800, it's not an ester, right? Because an ester has to have a C double bond O, which means it has to have a peak in the IR around 1700 to 1800. So lack of peaks tells you just as much information as presence of peaks do when you look at spectroscopy. Okay, so the intensity of a peak is related to the polarity. So C double bond O's are very polar bonds, right? So they usually give very intense peaks. C double bond C's are not as intense, so they usually give much smaller peaks. So the triple bonds, CN is a very polar bond, right? It's got a dipole, so it's going to have a very intense peak. The C triple bond C is not as polar because the two groups are the same electronegativity. If the C triple bond C looked like this, well, you wouldn't see a peak at all because that molecule doesn't have a dipole. So if you stretch the bond, it doesn't change the dipole, so you wouldn't see a peak in a case like that. But if you had a molecule like this, where it's not symmetric, then technically now it has a very small dipole, but it's not very polar. So the peak that you see may not be very big, and it may get lost in the noise, right? Maybe it may be so small that the peak gets lost in the noise. So IRs can be difficult to interpret sometime because you have to be able to discern is something a peak or not, or is it just noise in the spectra. So along those lines, if you had double bonds, alkenes, So which is more polar? So cis-alkenes are more polar than trans-alkenes. So the cis-polar double bond would be a little bit more intense peak than a trans double bond. But again, they're not very polar to begin with, so the peaks are usually only very weak for an alkene to moderate intensity. But a C double bond O is obvious. The peaks are usually absolutely huge and they're easy to pick out. Okay, so let's just briefly talk about what some of the different functional groups look like. So if you have an alcohol in the molecule, well, you have a peak for the OH, and that peak can be sharp and intense, but usually it's not. Usually it looks like this. Usually it's fairly broad. So why the difference? Well, if you have an alcohol, well, of course, what an alcohol can do is make hydrogen bonds, and that tends to broaden the peak out. So if you went to very dilute conditions, that would disfavor hydrogen bonds, because if it's really dilute, then two molecules can't find each other. If two molecules can't find each other, they can't make a hydrogen bond. Or if you go to high temperatures, that would tend to disrupt hydrogen bonds. So if it's not hydrogen bonded, the peak's going to be sharper. But usually in most samples that you're working with in organic chemistry, it's concentrated enough that molecules are going to make hydrogen bonds, and you're going to see broad signal for the OH. Or the same is true for the NH. For the OH of a carboxylic acid, it's typically give extremely broad OH signals. It may be so broad you can't even tell if there's something there or not. It may almost just be look like a straight line, but usually you can see something there. Usually it's just really, really, really broad. And the reason why is because carboxylic acids form really good hydrogen bonds. Right, they could make hydrogen bonds. They can dimerize in solution, so they typically they make very strong hydrogen bonds, and that often leads to very, very broad signals for the OH of a carboxylic acid. But if you have an alcohol as well, you also have the CO bond, so you have peak at 1200. And if it was aromatic, then you would have the 4 peaks. So if it's a phenol, if it's attached to a benzene ring, then you have the 4 peaks between 1500 and 1600 to go with it, right? Plus you have the CO single bond around 1200. And if it's carboxylic acid, you also have the CO single bond, so you have a peak around 3300 to around 3400, but very broad. And you have the OH, the CO single bond, and you have the CO double bond around 1750 inverse centimeters. So conjugation changes things. So if you have a p orbital, so that's sp2 hybridized, p orbital, p orbital, p orbital, p orbital. So if you have your carbon oxygen double bond right next to another carbon to a carbon-carbon double bond, so they're said to be conjugated. That changes things. So a normal ketone, this may have a signal around 1750, for example, but this C double bond O would be around 1660 to 1680. And the reason why is because you have resonance structures here. Right, you could draw that resonance structure, so there is some single bond character. To the C double bond O. So CO single bond, of course, is at 1200. And CO double bond with no conjugation is around 17 to 1800. So if you put something in conjugation with it, then that gives it some single bond character. That's going to shift where that signal is at towards the 1200 end. So you see it shift to smaller wave numbers. Okay, so for amines and amides, so the NHs, so NH is around 3400. Right? So it depends on, you can discern between a primary, secondary, and a tertiary amide in IR. So amide or amine. So this would be a primary amine because the nitrogen has 1 carbon attached. This would be a secondary amine because it has 2 carbons attached, or tertiary because it has 3 carbons attached. Same for the amide. 3 carbons attached, so tertiary, 2 carbons attached, so secondary, and 1 carbon attached, so primary. So the primary amines will give 2 peaks in IR because you have the symmetric stretch, where you can stretch the NHs in the same direction at the same time, or the asymmetric stretch, where one can compress while one stretches, right? So that would give you two different signals. If it's a primary amide, then you only have one NH. I mean secondary, you only have one NH, so you would only see one signal in the 3400 region. And if it's tertiary, there is no NH. So there would be no signal around 3400. So if you couple the different spectroscopies together, so mass spec, for example, if you did the mass spec and you saw that there was an odd molar mass, so then you would know there's a nitrogen present. But if you do the IR and you see that there's no signal around 3400, then you would know that this amine or amide doesn't have a hydrogen on it, so it's tertiary. Okay, and then for alkyl halides, so for the carbon-halogen bond, so it could be carbon-chlorine, bromine, fluorine, iodine, so those stretches are around 500 to 900 in inverse centimeters. So I didn't make this point up here, but this region of the IR spectrum. So from about 400 to about 1500 inverse centimeters is what's known as the fingerprint region, and it's usually very complex. So it's very difficult to interpret because that's where all of the bending modes are at. So it's hard to discern if you have a carbon halogen for that reason, unless you're really good at IR spectroscopy and you really understand it really well and you can see all of these little nuances, but otherwise it can be difficult to interpret that region since there are usually so many peaks in the fingerprint region, but not so many peaks in the rest of the region. So from about 1600 to 4000, it's not convoluted, so it's pretty easy to tell if you have a peak in that region, and so you immediately know what it's due to without having to do much interpretation if you simply have this information memorized. Okay, and then so ethers, you would just see the main peak would be the CO stretch. Of course, you have CH stretches, right? But all organic molecules have CH stretches, so these would all be around 2900. So you don't get a lot of information out of that region unless it happens to be on an sp2 or an sp hybridized carbon. But for sp3 hybridized carbons, the CH stretching region is not going to help you that much. If it was an ester, right, you got the CO double bond, so that has a peak. You got the CO single bond, so that has its own peak. Okay, so just a couple of examples of the utility of IR. So if we had these two molecules, for example, so what would the IR look like? Well, you have a bunch of CHs. So you have signals around 2900, and you have the CO double bond, so around 1700. So you'd see a signal around 2900 and 1700. And all of the CHs, of course, in this molecule are equivalent, but it doesn't really matter if they're equivalent or not. IR peaks are broad enough that usually they would just all be bunched together. So that would be your CH, and this would be your 1700, so that would be your C double bond O. And so if you had this molecule, so for the CHs here, you would have the 2900 and the CO around 1700, but then you have this additional peak, because that's around 2800 if the CH is on an aldehyde. So you'd have that, and you'd have that, and you would have that. And so even though these are both C3H6O, so that would be difficult to tell the difference between them in mass spec because they have the same mass. So the parent ion peak would be the same in the mass spec. So unless you had a fragmentation pattern, unless you knew how to interpret fragmentation patterns, it would be difficult to determine which molecules which use a mass spec, but it's easy in IR because of that extra peak due to the CH of the aldehyde. So that's another example if you had these two molecules. So they're both C4H8O. So that could be difficult in mass spec to figure out which is which, since they have the same molar mass, same parent ion peak. But if they did fragment, and you could interpret fragmentation patterns, and you might be able to figure out which molecule is which. But it would be easy in IR, because in this molecule, you just have the CHs. So you got the CH stretch around 2900, and you have the CO single bond stretch, which would be around 1200. Whereas if it was the ketone instead, then that would be around 1700, and there would be no peak around 1200. So if I gave you a bottle of these two molecules, didn't tell you which one was which, and I gave you an IR instrument, you could sit down and record one IR and know which molecule is which. Because if you have a peak around 1200, it's the ether, and if you have a peak around 1700, it's the ketone. Okay, so just another example, so these are both C5H12O, easy to tell the difference in IR because this has an OH, so that's going to have a peak around 3300, and this is not. But they both have CO single bonds, so they both have peaks around 1200, and they both have CHs, so they both have peaks around 2900. But if I gave you a spectrum like this and ask you to interpret, then I would ask you to assign all of the signals. So that means I would want you to say, okay, this is a CO single bond, so this would be that peak. This is an OH stretch, so this would be that peak, that bond. And then this is all of the CHs, so all of these CHs, and they're all pretty similar, so they're all going to be, all of the CHs in the molecule are going to be buried underneath the peak around 2900. Okay, so lastly here, you have what are known as IR correlation tables. So this is just a table to summarize where peaks are at. So, it just summarizes where all of the different stretching and bending modes occur for different functional groups. So for a ketone, so it may tell you, for example, for a C11O of a ketone, it has a peak, maybe it's around like 1720 inverse centimeters, and then it'll give you this code, whether it's SM, W, or BR, meaning whether it's a strong signal, a medium signal, a weak signal, or a broad signal. So this would say it's a strong signal around 1720. It typically give you a range, like 1740 to 1710 centimeters, inverse centimeters. And so when you're having to solve IR problems, you'll have a correlation table that you can look at to look up where all of these different peaks are at. But this is not that much information. I recommend just memorizing it, especially for those of you, again, who want to go on to medical school, dental, or pharmacy school and have to take the PCAT. You would just be expected to have this information and that table memorized. Okay, so that's the basics of IR spectroscopy.